So in this, we're going to go through a net ionic equation and then use that same equation to do a limiting reactant practice problem. We're going to break this down into really two parts. We'll call this part one right here, where we will be looking at this original equation where I just give you two reactants, aluminum and copper 2 nitrate, and then taking that, writing the products, balancing the equation, and assigning phase labels. Then we'll determine what type of reaction it could be classified as. There's going to be two types here. From there, we will write the net ionic equation, the complete ionic equation, and then net ionic equation. Then I'm going to make another video where we use that equation from above to go through this problem here. If 21 grams of aluminum and 160.0 grams of copper 2 nitrate were reacted, which will be the limiting reactant, and then what is the theoretical yield of copper, and finally, we'll calculate percent yield with this given amount of copper that was quote unquote produced in this reaction. So let's start off right here with solid aluminum and copper 2 nitrate aqueous reacting with each other. And maybe as we go through this, we'll just talk about what type of reactions this are as well. So right away, we can see that we have a individual thing, this solid aluminum, and then we also have copper 2 nitrate, which is an ionic compound that's aqueous. So if we were to zoom in on this on the molecular level, you would see copper ions with a +2 charge floating around, and you would see nitrate ions with a -1 charge floating around. Just kind of review from before a previous section. We know that this copper has to have a +2 charge on it because nitrate has a -1 and there's two of them. So altogether we have a -2. And in an ionic compound where we don't see a charge written anywhere up here, there is a 0 overall charge, meaning that the charge of, in this case, the cation or the positively charged ion has to equal out that, or zero out maybe, the charge of the anion. So that's where we get copper as a +2. I've been calling it copper 2 nitrate, and that is because copper is one of our variable charged ions that can either be a +1 or a +2. So anyway, we'll just leave that alone for now. I'm going to put that +2 back in here because as we go through, this is a single replacement reaction. Which means that this aluminum is going to swap out with the copper, meaning that we're going to get on a reactant side, our product side, aluminum nitrate. And I'm just going to write it as this for now. I'm not going to bring over subscripts. I'm just going to get my products written, and then I'm going to use the charges of these ions to figure out how many of each need to be together to get that 0 overall charge. I'll leave room for a phase label, leave room for a balancing coefficient, and then what we're left with our other product is copper. And this is going to be solid copper. Now to figure out what the, clean that up a bit, what the number of aluminums going with each nitrate or nitrates with each aluminum is going to be, we need to go to our periodic table. Aluminum is a main group element in group 3A, which means that it has 3 valence electrons, and when it loses those 3 valence electrons, it's going to get a +3 charge. Nitrate is one of our polyatomic ions that we have to have memorized here and need to know the charge. It has a -1 charge. So in order to balance this out for charges, we are going to need 3 nitrates. And to say that we have 3, we need to put parentheses around NO3 and drop that 3 in right there. So we're pretty much set up as far as what our products are. We can assign phase labels right now. If you go to a solubility table, whether it's one that you're given on an assessment that you have, or if you are looking online, you'll see that whenever anything includes nitrate, it's going to be soluble, which is the same as aqueous or AQ. So our two products are aluminum nitrate and solid copper. Now, the last thing that we need to do is to balance the equation. And I'm going to erase some of this stuff, and we will come back in and put these balancing coefficients, just so we're a little cleaner with this. What I'm going to look at first is my number of nitrates. And on my reactant side, I have 2 nitrates. We see that right here. And on my product side, I have 3. Now, to get these balanced out, I'm just going to keep nitrate together as a compound. I'm not going to make an atoms list with nitrogen and oxygen. And to get the same amount of nitrates on each side, I need to put a 3 in front of copper 2 nitrate, and I need to put a 2 in front of aluminum nitrate. This then gives me 2 aluminums on my product side, so I need to place a 2 in front of the solid aluminum. And on my reactant side, I have 3 coppers, which means that I need to put a coefficient of 3 in front of the solid copper. Now in this next question, what type of reaction could this be classified as? We said single replacement, and that's because the aluminum is replacing the copper as paired with the nitrate. Now it's going into solution. We'd see a precipitate of solid copper coming out. So this could be precipitation reaction. And maybe actually not. We won't say that because there is a solid there. By definition, precipitation is 2 aqueous solutions going together to make a solid. And we usually see that with our double replacement. But the other type is a redox reaction. And we will look at that as we get to our net ionic equation. So we'll go through and figure out what is oxidized and what is reduced, where, just as a reminder, oxidation is loss of electrons. Reduction is gain of electrons. And I'm abbreviating electrons as E minus. Sorry that my E's kind of look like C's. You'll get it. When we write our complete ionic equation, one thing that we need to do, or what makes it a complete ionic equation, is anything that has an AQ phase label, we'll just say breaks up. Because if we were to zoom in on this aqueous solution, we would see that there are copper ions and nitrate ions floating around at first, and then at the end there would be aluminum ions and nitrate ions floating around in that solution as well. So we break everything up, which means we're going to write them with their component charges. And this is going to be pretty long. Anything that's solid stays together or just stays as it is. So we're going to have ALS, so solid aluminum, plus, if we look back at our original equation, we have 3 copper 2 nitrates, which means we're going to have 3 Cu 2 plus. We're going to include that charge, and then aqueous, include the phase label, plus a total of 6 nitrates, because we have 3 NO3 2s, so a total of 6, NO3 minus, aqueous. And again, we're including those charges on the things that we split up. Anything that's aqueous, we break it up, and let's add a little note here and say, and include charges. If it is a solid, liquid, or a gas, it doesn't get broken up in a complete ionic equation or a net ionic. Let's see. Now we're over to our product side. So aluminum nitrate is aqueous, which means that we are going to break that up into its component ions. So 2 Al, 3 pluses. Those are aqueous. Plus 6 nitrates, NO3 minus, those are aqueous as well. And copper is solid, so plus 3 Cu S. And right there we have our complete ionic equation. Everything that was aqueous is broken up. Everything that was solid stays together as it was, which is really kind of simple here because what was solid is just a single atom. Now there's more than one atom in there, but it's just represented by its elemental symbol. Now in the net ionic equation, what we're going to be doing is looking for things that show up on both sides of the equation. In this case, we have 6 NO3s showing up on both our products and reactants. We call those spectator ions, and we are going to exclude those spectator ions when we write our net ionic equation. So spectator ions are here and here. Those are things that show up on both sides of the equation. We notice we have 6 of them. They cancel each other out. They didn't actually participate in this reaction, but rather just were there, present the whole time. And then we can write everything else in. So in our net ionic equation, we have 2 aluminums that are solid. We have 3 Cu 2 pluses that are aqueous. We go to produce 2 aluminums that are aqueous, so Al3 pluses, aqueous, and 3 solid coppers. This is our net ionic equation, and as you look, think ionic, think charge. On both sides of the equation, we would have a total of a +6 charge. So you don't really lose charge anywhere in this. But what this is showing us is that aluminum started off with a 0 charge on a reactants and went to a +3. If something gains electrons, it's going to get a minus charge. But in this case, with aluminum getting more positive, it means that it lost electrons. So we can say that aluminum was oxidized, which means that copper had to be reduced. You can't have oxidation without reduction. And looking at our net ionic equation, we go from a +2 on copper to no charge at all. So it means it gained some electrons at that negative charge in order to get to a 0 overall charge. So again, just kind of zooming out, what we did is we took our reactants, we wrote the products for this reaction, we assigned phase labels using our solubility table. Copper is just by itself, it's going to be a solid copper. If it had a charge, it could maybe be aqueous, but as Cu, just by itself, it's going to be solid. We identified that this is a single replacement, also called sometimes single displacement reaction. We identified that it's an oxidation reduction reaction or redox reaction where aluminum is oxidized, copper is reduced. We wrote the complete ionic equation, breaking up anything that was aqueous and keeping anything that was solid, liquid, or gas together. And breaking up, again, just means writing it as its component ions, which in that case, we needed to know what the charges were, which we kind of already took care of in that first problem here when we had to write the products. Then in writing the net ionic equation, we excluded spectator ions, which are found on both sides of the equation, to end up with a equation that was 2AlS plus 3Cu2 plus aqueous goes to 2Al3 plus aqueous plus 3Cus. We have the same number of each atom on both sides. The charges are the same on both sides. Overall charges, I should say. The overall charge of both sides is the same. And we're done. Now, in the part 2 video, we're going to use that equation from the top and go through a limiting reactant problem where I give you starting reactants or the masses of the starting reactants and have you figure out the theoretical yield of copper, and then